This is video number 3 in our series Topics in Tensor Analysis. A reminder, the playlist for the videos is featured at the website digital-university.org. During our first two videos, we explored some of the basic properties of covariant and contravariant components of tensors. And in this video, we're going to review some of those concepts and then also take a look at what is involved for a mixed tensor, one that has covariant and contravariant components. Now, remember from our previous videos that we're working with two generalized curvilinear coordinate systems. We have our axis labeled as x1, x2, x3, x4, and so forth, using superscripts to denote the particular coordinate axis. And this is the x-coordinate frame, or the x-coordinate system. And then down here, we have a different set of curvilinear coordinates, our y-coordinate system. And we assume that if we know, say, a vector that's expressed in the x-coordinate system, that we can take any one of those components of the vector and determine what it is in the y-coordinate system. And it goes the other way too, that if we have a vector in the y-coordinate system, we can take any component of that vector and with our transformation equation determine what it would be in the x-coordinate system. Now, in the first video, we considered what happens if we just have, say, a small displacement vector in our x-coordinate system. So let's just draw the x1 and the x2 coordinate axis. x1 looks something like this, and x2 is something like this. And we should suppose that there is a small displacement vector that we called dx. And our displacement vector dx, we noticed, would have a component on the x1 coordinate system and a differential component on the x2 coordinate axis, and also for all the other axes that are present in our x-coordinate frame. And let's just say that in general we have d number of coordinate axes, so that any vector that's in the x-coordinate system has a d number of components to it. Well, this same physical entity, of course, can also be expressed in the y-coordinate system. And that too would have differential components along the different y-coordinate axes. Now, what we established in the first video was this formula. Where here we have a particular component of the displacement vector in the x-coordinate system, and by taking these partial derivatives and summing over this repeated index, that gave us the corresponding component of the displacement vector in the y-coordinate system. And we notice that when we have a repeating index like this, in each case it's a superscript, but down here it's in the denominator, so we have sort of an upper-lower repeated index that automatically means we're summing over that index. So m equals 1, then m equals 2, then m equals 3, all the way out until m equals d. So this formula right here is really representative of this set of equations. Here we have n equals 1, so we have dy1, and then we're taking the partial derivative of it with respect to x, where m goes for 1, 2, 3, and so forth until we get to the last coordinate. And the same thing now, n can be 2, and then m varies from 1 to 2 to 3, and so forth, all the way down to the last component of the displacement vector in the y-coordinate system. Here we just have that represented by d, then m equals 1, 2, 3, and so forth. So this equation here with that repeated index really is just a very succinct way of writing this whole set of equations here. Then what we noticed in the first video is that we generalized. We said, well, suppose that in general we have a vector in the x frame, and we want to know how would the components of that vector transform into the y frame. And to do that transformation, if you have to use the same set of derivatives as what we did for the displacement vector, well, here we're in the x frame, and here we're in the y frame. So that the components of this vector transform from the x frame into the y frame, completely analogous to the way that a displacement vector transforms, then that is called a contravariant vector, and we denote its components with a superscript. So that was the basic idea of the contravariant components of a vector, or of a contravariant vector. And again, here is our repeated index. Then in the second video, we kind of took a different direction. We reviewed the basic concept of what a gradient vector is. And we just use a simple two-dimensional system to do that. And here then we know that this is a gradient vector right here. And it can have, we're in a two-dimensional system here. If we were in a d-dimensional system, then we just have more terms to add on to it, but have exactly this same form right here. So what we notice is that from our second video, we had this kind of a formula. The partial of the sine with respect to yn equals the partial of xm with respect to yn, the partial of psi with respect to xm. And again, that just follows directly from the way a gradient vector is set up. Partial of psi with respect to x1, partial of psi with respect to x2, where psi was some scalar quantity that in turn depended upon the x1 and the x2 values. So this was the component of a gradient vector in the x-coordinate frame. This was the component of a gradient vector in the y-coordinate frame. And again, we see this repeated index here. So this is repeated now from m equals 1 to m equals 2 to m equals 3, and so forth, so that this equation right here is really representative of this set of equations. Well, here we have, start with n equal 1, and then for the m value, it goes from 1 to 2 all the way on out to d. And then for n equal 2, we'd have it like this, then m equals 1, m equals 2, on out to m equals d, and then our gradient vector in the y-coordinate frame, that's going to have a d number of components, so we're down to the last component here, and again, m equals 1, m equals 2, on out to the last coordinate. So, and again, this whole set of equations here is just encapsulated in the single equation, realizing that m is a repeated index. So here we have a gradient vector that's in the x frame. Here's the gradient vector in the y-coordinate system, and here's how you can relate the two. Then what we did was we generalized upon that concept. We said, well, suppose then that we just have some vector in the x frame, say w, and we want to know if we know a component of that vector in the x frame, what is it in the y frame? And if in order to make that transformation, you have to use these sets of derivatives, then that is a covariant vector. And again, we're denoting, here we're in the x frame, so we have it like this. We have an m component. Then in the y frame, we have an n component. So here we have the vector in the x frame, and the components of that vector transform into the y frame by taking these partial derivatives and then summing over this repeated index, just like we did previously for a gradient vector. And if they transform like that, analogous to the way a gradient vector transforms, that's called a covariant vector, and its components then are denoted with the subscripts. So from the first two videos then, we considered the basic properties of contravariant and covariant vectors. Again, a contravariant vector in general would look like this. Would have this type of transformation property. And this is a contravariant, and the covariant in general would have this type of transformation property. Try to get this in better focus. Okay, a contravariant vector and a covariant vector. This transforms analogous to a displacement vector. This transforms analogous to a gradient vector. And notice how this is set up. Here we have a vector in the y frame, and we're considering an nth component here, and the n is a superscript. So when we're doing this, then the partial derivative for y is going to be in the numerator, because the n up here is a superscript. Here, this component is a superscript, but now it has to appear in a denominator because this is the vector that has the repeating index component. So if the m is here, then it has to appear in the denominator down here. Here we're in the y frame where the n appears upstairs, so it has to appear upstairs here. So you know that the partial with respect to y is going to be in the numerator. Here we know that the product with respect to x, the m, has to appear down in the denominator because it's a superscript here, but this has to be our repeating index. So that's sort of like the general pattern then for a contravariant vector. For a covariant vector now, here then we are in the y frame, but the nth component now is down here as a subscript. So we know then that it has to appear in the denominator because it's downstairs here. Here our nth component is down here, but this is the one that carries the repeating index, so that it has to appear upstairs over here in order to have the proper pattern to it. So here we're in the y frame, but the n component of that, if you will, that has to appear in the denominator. So the partial of y is going to be in the denominator. The partial of x is going to be in the numerator, where that m then carries along with it as that superscript, so we can have our proper repeating index. And that is sort of the general pattern then for a vector that transforms in a covariant fashion. Now, what we did in the first video, we considered in general two types of contravariant vectors. We said, suppose we have a vector A, and this is a contravariant vector, which means it would transform something like this. Okay, it's y, it's in the y frame, this is upstairs, so the partial of y has to be upstairs with the m component, and then we have it in the x frame like this. The partial of x is going to be down here, and now we're going to have our repeated index. We can call it r if we want. So a general expression then for our contravariant vector could be like this, and then we could have another contravariant vector. Let's say we'll call this n. We're in the y frame. In the y frame, and the component appears upstairs, so this has to be in the numerator. X is going to be downstairs, we know that. And then we have b, x, and then our repeated index, we can call it s, and it has to be in the denominator here, so we get the repeated index like this. Okay, so here then we would have an expression for two covariant vectors. And in the first video we considered what happens if we multiply these together. So we have it like this. Make sure that we're keeping things in focus. Now, when say we multiply them together, what we mean is this. This vector has a d number of components. This vector has a d number of components. We can take any component from this vector and multiply it by all the d components that this vector has. Then take another component from this vector and multiply it by all those d number of components that that vector has, and do it for every single component here. So what we're going to have then is d number of components times d number of components, so we're going to end up with d squared number of components. Well, we can symbolize that just simply by this. And here then we don't have to have the a and the b. That's not important. It's the components that are important. So the multiplication of these two vectors we can symbolize like this. But let's go back up here to our expressions. That would be equal then to this times this. So we have the partial of y with respect to m, partial of x with respect to r times this, the partial of y, and partial of x, s, and then we have this times this. And here, again, this has d number of components, this has d number of components, and we're multiplying those components together. So we can symbolize that again as just t. We're in the x frame, and we're multiplying all these components together. That would give us a total number of d squared number of components. And then we'd have this in between. And then this, as we notice from our first vector, this was in general how a contravariant vector transforms. Now what we want to consider is how does a covariant vector, or not a vector but a tensor, because here we have then two different components that we multiply together in each case. So this is a second order tensor, and this is a contravariant one. What we'll do is we're going to stop the video here. We're coming up on our time limit. But we're going to come back and we're going to look at this pattern a little bit more closely. Then we'll look at what it means to be a covariant tensor, and then consider some of the basic properties of a mixed tensor. So come back, join us for that video, and we'll round off our discussion.